Thanks. You know how far he was going to get the adapter? He was going to give me a remote control adapter so I can run around more. So are most of the seminars recorded?
Most of them recorded.
Are they posted publicly somewhere?
YouTube channel. We have YouTube.
You have a YouTube channel. Is it the TGDA?
No, Western Math. Western Mathematics.
Oh, I see. Math. Any good ones I should check out? I go hunt down this channel. No. I was going to watch one of the recorded lectures from this seminar. Which one should I look up? They're all, no, that's an okay question, because if they're all really good and you just can't choose which was the best. It's not like Celebrity Jeopardy, it's like name a number.
Will this help? Like, I have an adapter.
Does that help?
Is that USB and USB-C?
I think so.
Oh, maybe. Maybe let's try it.
I forgot you also have a Mac. I was looking for people with Mac there.
Oh, yes. Oh. All
Can we
right.
start, or is there something?
I don't know.
to press?
I don't know. No way to know. Yeah, we're the computer scientists in the room. We're supposed to do. There's a couple others here.
Okay, towards the beginning, the important introduction part.
Let's try this one. Well,
You can watch it on YouTube later.
yeah, so it doesn't let us know if it's recording or not. Oh, you think this is it? It is recording. It's actually already been recording. All our banter is thoroughly archived. Go ahead. We'll let the editor cut out the beginning. Go ahead.
All right, so it's great to have Don Sheehy here. I mean, he's an old friend. I think he was here many years back, 8 years or something like that before. So Don did PhD from CMU with Gary Miller, and he graduated in 2011. After that, he went to University of LA for a couple of years, and then he joined UConn as a faculty member there till last year, when no, actually this summer he moved to North Carolina State University now, as a faculty member now. And so Don has done a variety of things focusing on geometry and topographic reasons, spanning from the early days on the meshing kind of questions, from the geometry questions, now to more in addition to local quantities. And many of us here, and from my group, definitely, we look at his work on data specification, approximation of the Victoria distribution complex. So today he's going to talk about something relating cohomology, parallels of triangle, and all the fun stuff.
All right. Well, thanks so much for the invitation. All right, so this is a picture you probably recognize. Does anyone know who drew this picture? Some guesses here.
Azure.
Yeah, everyone says Escher drew this picture. Escher did not draw this picture. Escher copied this picture from Lionel Penrose. So this impossible staircase going up, 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 and up was in some sense inspired by Escher because Roger Penrose, the son of Lionel Penrose, perhaps maybe more well known to some of you from things like Penrose tilings and things like that. Roger had gone and seen an Escher exhibit and wanted to start drawing interesting, impossible figures, and he was playing with these ideas and talking to his father, and his father drew this one, which appeared in this article, Impossible Objects, a Special Type of Illusion. And then someone sent the article to Escher, and then Escher's particular example of the staircase with the men going up and up and up, or maybe they're going down and down and down. I can't remember if that picture is optimistic or pessimistic. Maybe even if you're going up and you still end up in a circle, maybe either way it's pessimistic, I don't know. But that actually was inspired by this figure. So later, Roger Penrose wrote, let me just highlight the year. So, no, this is 1958. So many years later, Roger Penrose wrote an article about relating this concepts in these impossible figures to notions in cohomology. And I'm going to talk a little bit about that paper. I'm going to try to tie it back to some work that was done much, much earlier in the 1860s by James Clerk Maxwell. And I'm going to try to also tie it into some of my favorite problems. Now, part of the reasons for the organization of this talk is that I wanted an excuse to tell you about some of my favorite problems that I don't know the answers to. So most of this talk, I won't be talking about new results. I'm going to be talking about some very, very old results, but possibly in a new light. And I had this vague hope that having to give a talk about it, I might finally crack some of those old problems. And I didn't. So you'll get to see these problems, and if you have ideas about them, I'd love to hear about them. All right. So Lionel Penrose, by the way, so he was a geneticist by training, and from his book, The Biology of Mental Defect, he was looking at genetic aberrations and how they result in some physiological differences. So you just look at these pictures from his book, and you know that this guy would have loved computational topology, like modern computational topology, to be able to actually quantify these shape changes in say, hand shape as a function of some genetic differences. But the key thing there is that he was a biologist, his son was a physicist and a mathematician. Neither of them were psychologists where this article was actually published. So the story goes, according to Penrose, that they wrote this paper just out of a kind of play, and then they had no idea who would ever publish it. And so, but his father said, you know what? I have a friend who's the editor of the British Journal of Psychology, and I'm sure they'll publish it. And so he says, and so it became a psychology paper. But what's kind of neat is that psychologists embraced it as a psychology paper, and it has some interesting psychology in it, because you have to think about what is it that you see when you look at this. Like, what do you understand as being, like, it looks like a real thing. You feel like it's like this could exist, and then you look somehow at it long enough and believe that it can no longer exist. And they do all kinds of tests, like they try to see if like monkeys get confused by this and stuff like that. So it exists in the psychology literature now, but it also has some interesting mathematical side. So the paper about cohomology in these figures was 1992, so much later. And this figure, which Roger Penrose thought of as kind of the quintessential example of the kind of optical illusion he was interested in, is sometimes called the Penrose triangle or the impossible tribar. And there are a couple things that he really liked about this. I'll just highlight one of them. He called this a pure optical illusion. And what he meant by that, well, what he says is that if you add more detail, like adding this shading and stuff, actually only makes it more compelling. that it doesn't reveal any kind of trick by adding shading. It actually sort of looks even more real. But the cohomology comes in the following way. So he says, when we look at it, what happens is we look at one part of it. So here's a picture of just like one corner of our impossible tribar. This figure is taken from this paper. And you look and you imagine that there's some object sitting out there in 3D that you're looking at. And it makes sense and it's believable, and you really say, like, in this little patch, I really believe that there is an object that I'm seeing a picture of that projects onto this plane. Maybe I don't know how far away it is, right? It could be here, it could be here, but up to just some scaling of the distances, maybe I know what I think I see. Okay, and that's true everywhere locally. So as your eye kind of goes around, everywhere at any patch you look at, you believe that there is a 3D object that it could be the projection of. And so you have a cover of this shape where everywhere in the cover you have an interpretation. And so what happens is, let me get back here. So if you look at points that overlap in the cover, you see that actually if I look at one cover element from here to here, if I have some idea of how far away this is, then I have an idea of how far away this is, because relatively, because I imagine if I have, so I have some idea of what that cover element looks like, but now I want to somehow glue them all together. And what happens is he says like these, you get a co-boundary. I'm sorry, you get a co-cycle here, and you want to check, in order for it to be resolved, you would actually have to be able to line up all three of these together, in these three pieces of the cover, into one coherent object. And so if it's actually a real, if there's a real object, then that co-cycle will be a co-boundary. And so he gets to this key statement here, which I found so compelling, it's really kind of exciting, is that he says the test for whether or not the figure depicted here is impossible is whether or not the resulting element of this first cohomology group is indeed the unit element. Now, it's a little bit funny. I don't know if you like writing cohomology in terms of the multiplicative group of real, non-negative reals, positive real numbers. And the reason he's doing that is because he's thinking in terms of perspective drawing, right? So that the differences are just scaling. So what he calls the ambiguity group, right, which is the group over which he's taking cohomology, is the distance. Right? That's what has been projected out. Okay. So I got really excited about this when I first read it, because I thought, oh, this is cool, because now I have this picture that someone's given me that's clearly some kind of discrete topological object, right? I can see these nice faces. In this case, it's just a cover, and we're looking at actually the nerve of this cover, right? So we're going to get this 3 vertices and 3 edges and a nice triangle. And I'm going to do some topological computation. What it looks like, I'm going to check some particular co-cycle and check if it's a co-boundary or not. I'm going to do a topological computation that's going to tell me that it's impossible or not. But that's actually not what happens. I found this really disappointing. Partly because you can't really do that computation exactly. What you can do is you can prove that this thing is impossible, and what you get is it's kind of in some ways the opposite, right? You look at this figure and you realize by some other means that it's impossible, and you instead conclude that there must be some non-trivial cohomology. But unfortunately, that was kind of obvious. You knew you had this cover with 3 elements. You know that there's a hole in the middle. You know that it's just 3 vertices and 3 edges making one cycle. Like, you knew it had non-trivial cohomology. But what he's actually saying is that you couldn't have this kind of impossibility without a hole. All right? So you may have seen this kind of thing before, especially maybe a first introduction to cohomology sometimes goes through problems in calculus. We've seen this book, From Calculus to Cohomology. It starts with examples that are very much like this. And I'll try to draw some of those pictures and we'll see how it works. So, So here it is. He's saying, like, in the figure, there has to be a hole in order for it to be impossible. And like I said, let's say this one more time. It's saying that you first observe that it's impossible and you conclude that there must be a hole. So you go from something non-obvious to something obvious. And that's maybe not so satisfying. Yeah.
I want to ask the coefficient. Is it semi-group? The R class is not. You were having R class, right?
Yeah, under multiplication.
So, is it a ring or is it like what coefficients in what algebraic object? Is like a semi-ring?
This is a group.
R class?
Yeah.
In what sense? A group?
Under multiplication.
Oh, okay.
Yeah.
So it's open, open zero, right?
Yeah.
I see.
Yeah. All right, so let's dig into this. So, and then I guess he says, hey, you can come up with even more interesting examples as long as you have this hole. There's this wonderful, beautiful book called The Topological Picture Book by George Francis. And he explains kind of something like what you might be seeing as your eye goes around the Penrose triangle. Is if you go in the right direction, it feels like as you go around and around, you're always coming closer and closer to you. And this is where you get this feeling that it must be impossible, because if it keeps getting closer and closer and you get back to where you started, you must be closer than where you started, and therefore it must be impossible. That's why we look at it and we feel it's impossible. I'll give maybe explicitly why it's impossible. But this kind of idea, you see this in people have built these sculptures. Here's one in Australia, where if you look at it from just the right angle, right, it looks like you've really got this impossible figure. But from other angles, you see that it's wide open. It also shows up, if you've ever seen the puzzling stack exchange, I probably shouldn't tell the math department about this because probably some huge amount of math research gets derailed by visiting this website. But there's a puzzling stack exchange with these little puzzles, and their icon is supposed to be like a Penrose square, if you will, that's been opened up. And the idea is it's supposed to look like a keyhole. And this is like an icon for puzzles. Although I think it's not such a good icon for puzzles, because a good puzzle should look impossible from almost every direction. And this one is a case where it only looks impossible from straight on. So Penrose wasn't the first to draw these kind of figures. So Oscar Reuterswärd did a bunch of different images of impossible figures back in the 30s. This is the one that's sort of cited as the first of the impossible tribars. You see, it's a little bit different in that it's not just one connected piece, but this series of cubes. And later, Penrose actually wrote 2 articles about this. One is an essay in a book about the works of M.C. Escher. He tries to kind of defend his claim on the Penrose triangle. And one of the things he really emphasizes is that his figure is in perspective. That it's drawn in perspective, where this is just a orthographic projection. Actually, you can draw this in perspective as well. But he didn't, I think that there's a sense in which he could have defended his claim a little bit better, because one thing about this one is that it's not that impossible. Okay, so here is an image from a particular direction of this shape, and you see that we've sort of cheated. See that the faces are actually, it's just the back sides of the cubes. If you arrange them like this, then from the right perspective, it looks exactly right. But from other perspectives, you see something else, but you see that it's actually not so impossible. It's at least less impossible. And this one has an interesting story, because you can get like 3D prints of this. And the guy who first worked this out was selling 3D prints of it, and he would only show it from certain angles. And then when someone figured it out and posted it, their own 3D printing model, and it was the first case of a DMCA takedown notice. You know that the Digital Millennium Copyright Act allows you to try to claim that someone has infringed on your IP for a 3D model. Was someone trying to take this down. here's me holding some cubes. So part of the principle at work here, and this is kind of fun to do if you have two cubes, you glue one to your index finger and one to your thumb. Actually, that's not what you do. You just fold them like this. But it's really compelling how, like, you see once things that line up, you really believe they must, like, if they're parallel in the projection, you kind of believe they should be parallel in 3D. And there's a variation. I think you can get, I couldn't get this one right, but some version of just the cubes and some kind of impossible figures like this. Some of these are realizable, but really these are examples where, because the objects are disconnected, you're not really going to see, well, it's a little bit harder to reason about the faces here, because you can have this extra information about faces occluding other faces. And that's really what makes some generalizations of this problem quite difficult. But in the case of the Penrose triangle, there's no faces blocking other faces. But it is possible to make the Penrose triangle really connected if you again cheat some more. So here's a 3D model where someone like bent this thing around, and it looks okay, right? It's kind of like it's possibly gotten a realization of this impossible figure. But it highlights that we really want to say a little bit more clearly what the heck we mean by a realization, and so that we can say what we really mean by impossible. Right. So the framework I want to talk about is what I'll call lifting planar graphs. Right, so we're just going to have the drawing, a line drawing in the plane, and I want to lift it up. And what I want to do is I want to lift it so that all the faces stay flat. This is a really easy case because all the faces are triangles. Any way you lift up a triangle, it stays flat. But this is the case that's near and dear to my heart because this is a Delaunay triangulation lifted onto a paraboloid, which if you studied computational geometry, like this is a very, very important construction. And that's really where I got started in a lot of these problems. Now, if I'm going to do this lifting, another way to think of it is that for every face in the planar graph, I'm going to associate it with some affine function, which is just the plane that I'm lifting it up onto. Right? The plane is the graph of this function. And it has some gradient and then some z-intercept. This is all we're doing is just we want assignments of these functions so that actually they glue together at the edges of the faces and form one continuous function. Okay, so it's a continuous function on the plane that's piecewise affine. Now, if I were to just look at the z-intercepts, that gives me a lot of information actually, because what it tells me is that if there's a lifting, I can associate a real number with every face. And so I get an ordering on the faces. Okay, assume I don't get unlucky and have multiple intercepts at the same point. And I get to choose maybe where the origin is in the plane, which will change what these intercepts are. But if I choose it generically, then I'm going to get a total ordering on the faces. That's going to be really useful. And so let's keep that in mind. I'm going to give you just a very, very short interlude in where I came into these problems. As I was working on a problem called mesh generation. And that's where you're just trying to decompose a space into nice triangles. And you would think that problems with triangles and lifting should all be easy. You think that, well, I can always lift triangles up and they'll stay flat and the liftings will always exist, but we'll see that actually even those can get tricky. So in meshing, we have these conditions about trying to make the triangles nice, et cetera, and adding extra points. And there's a dual version of this. So this is what we would call a Delaunay triangulation because every triangle has an empty circumcircle and it's dual to these things called Voronoi diagrams, which hopefully many of you have seen. And there's a similar kind of quality notion for the Voronoi diagram. Now, both of these objects, both of these decompositions have in some cases, the definition is given in terms of a lifting. And in fact, the relationship between them is that they're kind of polar duals in their liftings. So they have this dual relationship as planar graphs, but they're also dual in a kind of projective geometry sense after you lift them. And the algorithms for constructing these often work with simple primitive operations like called flips. Okay, so here's a flip in 2D. That is, if I have two triangles like this, where their union is convex, then I can swap out these two triangles for these two. So I took that edge and I put the vertical edge out and I put the horizontal edge in. Okay, so going either way, these are flips. And you can build a graph from flips as follows. What you do is you take the vertices of this flip graph are going to be all triangulations of a point set. So it's a maximal planar straight line graph on the point set. So it's, and I have the point set, I draw as many straight edges as I can, so I can't draw any more. The faces will all be triangles, that's a triangulation. And every possible way that I can do that is going to be a vertex in this flip graph, and then I'm going to connect two triangulations if they differ by just one thing. The classic result is that in the plane, the flip graph is always connected. So any two triangulations of the same point set, you can get from one to another just by doing these very, very local operations. There's a corresponding notion of a flip in 3D and actually in any number of dimensions. In this case, I've got two tetrahedra glued together along a common face, and I'm going to replace them with three tetrahedra glued together along a common edge. Can you see it again? There it is. All right, so really what we're doing when we do these flips is if you imagine that this is 5 points in 3D. Well, if it was 5 points in 4D, that would just be a simplex. And that simplex would have a top and a bottom, which would be 3 complexes. And this is swapping between the top and the bottom of a 4 simplex. In the same way that this is swapping between the top and the bottom of a tetrahedron, if this is a projection. And so that kind of projection view from one dimension higher is really handy. All right, so you can build this flip graph, but the flip graph in 3D for a point set, it's not known if it's connected. And this is a problem that haunted me for the first couple of years of my PhD. And so you'd like to say, either find some point set and 2 triangulations where you can't flip from one triangulation to another, or find some cool algorithm that works. So the algorithm that works in 2D doesn't work in 3D. It's known that there's a kind of greedy algorithm that will flip you all the way from one triangulation to another. And in 3D, it's known it gets stuck, but for the example where it gets stuck, you kind of go back and find some other path, and it's still at least connected in that one example. So this is an open problem. There's cool connections in other areas of geometric combinatorics. Even just the case of points on a circle, right? So the triangulations of points on a circle, in this case, this is 5 points on a circle, and the flip graph is, you notice that it's just a pentagon. And here it's been augmented and treated not just as a graph, but as a 2-dimensional polygon, right? So I have the edges and also this 2-dimensional face, and those are also labeled with triangulations of the pentagon, but you see the higher dimensional features are sort of missing edges. And in terms of liftings, you can think of this where if I lift the points generically, I'm going to get a triangulation in there if I project down again this lower part of it. And if 4 of the points end up coplanar in the lifting, then I'll get a higher dimensional face. And if they all end up coplanar, I'll get this one. This is called this particular one is called the associahedron. It's part of a general kind of construction you can make called sometimes called the secondary polytope. And what's cool about this is that the edges are, in any number of dimensions, really will be just flips. But the problem is not all of the triangulations show up on the vertices of these generalized associahedra or secondary polytopes. So there's a subgraph of the flip graph, which is polytopal, that actually has vertices that are vertices of a polytope and edges, which are just edges of the polytope. It's a really amazing object, but there's just that it only captures the flip graph on a subgraph of the flip graph. And so what is that flip graph? Okay, so this is what I just said. 2D, it's connected. 3D, we don't know. D dimensions, we have this nice polytopal subgraph, and it just corresponds, the vertices we know, that is the triangulations we know how to connect by flips, are those ones which come from lifting the points up into a convex, shape, right? So the function we get from the lifting, this piecewise affine function, is convex. Those are exactly the ones we understand well, but some other triangulations may or may not be connected to those. Okay, so it makes sense to start thinking about those convex liftings. So I know there's always a lifting given a triangulation, but there might not be a convex lifting. So remember, if I have a lifting, then I'm going to have a total ordering on the faces. We're going to use that to show some examples of triangulations which don't have a convex lifting. Right? And this first showed up in a paper in 1990, which is a really cool little paper, which I think the computational topology community should probably revisit. We've thought a little bit more about some of these problems. And the paper is by Herbert Edelsbrunner. And he was interested, again, in looking at these kind of cycles of occlusion. He says, when does this happen? Because in graphics, if you're going to draw a bunch of polygons, there's an algorithm, I think it's called what, Painter's algorithm. Graphics people will correct me, but if you could just order the polygons from back to front, it would be wonderful. You just draw them to the screen in that order, and you just draw them on top of each other, and everything would be fine. But there's no total ordering if you have these kinds of cycles of occlusion. So, so what Herbert was going to show, and he did, is that at least for some really nice class of polyhedral complexes, you never get these cycles of occlusion. In particular, he's looking at things that have a convex lifting. And here's the idea. I'm going to draw the pictures here in, really these are this is the one-dimensional case lifted up into 2D. The idea is exactly the same in 2D lifted up to 3D, but it's harder to draw the pictures. Right? So if you lift up to planes, and they meet at an edge, they can fold one of two ways. These are called valley folds or mountain folds. I think this vocabulary is taken from origami. And so in a valley fold, if I'm going towards, let's say that this is the z-axis here. If I go towards the z-axis, then I cross a valley fold, then the intercept goes up. And if I go, again, towards the axis and I go across a mountain fold, then my intercept goes down. Okay, so I said that I have a total ordering on the faces from these intercepts. And so based on which way the folds go, it tells me locally what that ordering should be. Okay, so this was, yes. No, it's, oh yeah, so if they're planes, it's the same. So in the plane, actually, let me just, sorry. So if we're doing this in the plane, so I can at least do it this way. If I pick an origin, there's one. Now if I go from face to face, it's well defined whether I'm going towards the origin or away. Because I take the edge and it separates one of the points from the other one, or sorry, one face from the other. These are convex, they're triangles, in fact, they're simplices in general. And so there's a notion of going towards the origin or away, and the same thing should hold. So if it's a convex lifting, all the folds should be valley folds. So it tells me for every edge, I know that as I go towards the origin, that the ordering should go up, right? So going across an edge that brings me towards the origin should always go up. But if we extend these edges, you see, I drew this one in for us so we could really see that going from 4 to 5 should also go up. 3 to 4 clearly goes up, 4 to 5 goes up. And if we do them all, you'll see that the graph, the directed graph we get, that the ordering is going to be cyclic. So as we go around this Schoenhart triangle, just like when you go around the Penrose triangle, you're somehow getting closer and closer to each other if you have closer, or higher and higher in the z-intercept. So you have a total ordering, you have a cycle and a total ordering as your contradiction. So there doesn't exist any lifting of this triangulation so that all the folds are valley folds. There's no convex lifting. It's what we sometimes call a non-regular triangulation. They're also called, it would be, if you could do a convex lifting, they're also called weighted Delaunay triangulations. Heard that before. And they're also sometimes called coherent triangulations. So this one doesn't fit into that class. It's still connected in the flip graph, but there's no way to lift this up. Is there a question about this? It's kind of the key idea. So this is a cute paper, and so Herbert showed that you can do this in any number of dimensions now as well. The same principle works. In fact, I wrote it in this vector format for affine functions, so it's clear that there's nothing special about 2D here. So if you put this ordering on the in this case, the full dimensional simplices for any given origin, if you find a cycle in the ordering, then you know that that is not, that there's no convex lift. It's not regular. Yeah.
Is the triangulation on the impossible triangle, this one?
Yeah, so we should try, we'll do that. We'll try to figure out, is the same idea work to kind of show us what impossibility will mean? Because I think when we look at the Penrose triangle, we'd like the same notion of realization. We'd like to say that really when I want an object where the faces are flat and they meet along certain edges, and that's how I interpret the picture. And so we can try to do the same thing there, and let's see what happens. Yeah.
Is it possible that a triangle exists in 4D or a higher D? Or is it like it doesn't exist at all, never D? The triangle.
The Penrose triangle?
Yeah.
There are examples of kind of analogous impossible figures in 3D. And one thing that's cool is I think people have even found examples where the obstruction, if you will, is really from the two-dimensional homology and not from the one-dimensional homology. But actually, I started thinking about this. Again, this was also one of the problems that obsessed me when I first started my PhD, was every time someone talked about an example of a triangulation that was not regular, they gave this example. And only this example. Or some trivial like extension of it, like maybe a square twisted inside a square, or a pentagon twisted inside a pentagon. And so you start to wonder, are these the only bad examples? Like obviously I can make some big triangulation, stick one of these somewhere in there, and I know it will be impossible. But are there examples of impossible as non-regular triangulations where the set of edges which can't be simultaneously satisfied maybe don't form a cycle like this? And another way to say that is that acyclicity condition from the Edelsbrenner paper, is it necessary and sufficient to describe non-regularity? It probably isn't, but as far as I know, there's no known examples of triangulations which are not regular, but still satisfy this acyclicity. You have to be careful about it though, because if I were to do something like, put the origin somewhere else, I might not see the cycle, right? When the ordering is relative to the origin. So I kind of, if I was going to prove to you that a particular triangulation was not regular, I'd have to either, well, I would show you the right origin. Now, if I wanted to prove that it was regular and I didn't have, I guess the best way to show that it's regular would actually be to give the lifting. But if I just show you a bunch of places and I say, hey, look, it's acyclic from all these different perspectives, maybe you just didn't look at it from the right angle to see. Yeah, and it's a very, well, okay, yes, it's not too hard to see what it is, and in some sense, it's very old. I'm giving him a little bit more credit than the paper has, but James Clerk Maxwell kind of worked all this stuff out in the 1860s. And so I want to look at this other part of the lifting, which is to look at the gradients. So if I have a lifting, then, okay, so these gradients, let's say I'm lifting out of the plane, then this is a vector in R2. I can actually treat that as a point. So for every face, I have a point in R2. And I can use that to draw the dual of the planar graph. And so, because that's putting each face at a particular vertex, I'll draw a straight line between two of these vertices for every pair of faces that share an edge. And that's what James Clerk Maxwell called reciprocal diagrams. He was looking at how certain kinds of drawings are really these, what I call linear embedding of planar graphs. And the way it came about was he was looking at forces. So he had, just like you saw in like a first physics class, when you look at the forces acting on a body, you've got a collection of vectors. If it's an equilibrium, that those vectors sum to 0. So if they sum to 0, I can draw them end to end, and they'll come back to where they started. So there's a natural polygon associated with any vertex that's in equilibrium. And so he had a system of points and edges where these two, there's a force between two vertices if there's an edge between them. And if they were in equilibrium, then the force polygons, there'd be a force polygon for each one of these, and he wanted to draw all of those polygons at the same time. He said, I know how to get a polygon from a vertex in equilibrium, and so you kind of think of that as like a puzzle piece. He says, now can I glue them all together all at once into one diagram? And he was working out what the conditions you would need for that new diagram to exist, this reciprocal diagram. Now, I've already kind of spilled the beans here because I showed you that there's a drawing of the dual that comes just from the gradients. And in fact, that is a reciprocal diagram. So if there's a lifting, then there is a reciprocal diagram. And I think one other cool thing about this paper is that if you dualize figure 2, you get like figure 2 in Roman numerals. I guess he went from like uppercase to lowercase. There was no lowercase 2. And so, but this paper is really neat because actually it holds in it the seeds of a lot of more advanced math, right? Because he's really looking at this force system. It's really a kind of discrete one form that leads to a relationship to liftings, right? And that the existence of a lifting from the gradients, well, you know what that is, that's an antiderivative, right? So you want to know, if I know the gradient everywhere, is there a function that has that gradient on those faces? It just happens to be a piecewise constant gradient. And so he recognized this. The paper is a little bit, it's beautiful and terrible. There's no real proofs in it, and he doesn't really do the algebra. But he does make these observations, and you can see kind of where he connected the existence of the diagrams to the fact that maybe the diagram came from 3D, because he has these simple examples that actually the first simple example you do is a complete graph on 4 vertices, which is really just a tetrahedron. And you see that the tetrahedron is polar to itself and it satisfies the conditions he wants. But then if you try to do a graph on 5 vertices, if you draw out what the reciprocal diagram would have to look like, it turns out it's exactly the kind of picture you draw for a really classic theorem in projective geometry, which is Desargues' theorem. And if you've seen Desargues' theorem, at first it makes no sense if you look at the statement. And then if you understand it as the projection of something in 3D, it's almost a completely obvious, feels like a tautology. So, so he made this connection between these forces and liftings. All right, so what does that do for us for Penrose though? So now if we're gonna use this definition about that a lifting is what we want, a realization of this in 3D as a real object is gonna be a function on the plane, or at least on some subset of the plane. We don't need a function on the whole, such that it's gonna be what, affine on the faces, and there's 3 faces here. And the whole is, has sort of a weird shape. I claim it's not a triangle. The hole looks like a triangle, it's not a triangle. The hole is the triangle plus these edges, because when you look at this picture, you have no expectation that the function is going to be continuous from here to here. Right, actually, that's how the shading helps us a little bit. So if I was looking for something like that, what I might do is, well, here are my three faces. I'm going to apply the same idea from Edelsparner. I'm going to look at the edges. I'm going to put I need an origin here. I'm going to put, let's put the origin maybe in the middle. And so as I go from face to face, it's going to give me an ordering on the faces. Now, but this is, they have to be really careful here, because I've made these all valley folds. And when I look at it, I kind of interpret it as valley folds, that they seem to be folding away from us. But maybe we want to avoid that kind of weird case that we saw from the Reuterswald example with a 3D print, right? Where some of the faces, maybe they're bending the other way. Maybe there does exist some version of this. I just have to fold some of the vertices in the, I'm sorry, fold some of the edges backwards. Maybe it exists. So if I had taken the perspective out here, then okay, it's not, I don't have a cycle. But if I make one of these edges fold the other way, then from this perspective, I again see that it's cyclic. Right? And it just needs to be cyclic from one particular choice of the origin for it to be impossible. And so I guess up to symmetry, maybe this is the only case I needed to check. Right? Because if I had made this one a valley and these two mountains, it would just be cycled the other way. And then I'm going to rely on your visual intuition that these are the only two cases, either where all the folds are the same or just one is different. And so you can kind of use this idea to give a proof now that there's no way to realize this shape with flat figures. Okay. Again, it is maybe, we go back to psychology, right? This is one that you already knew it, you felt it in your bones, right? That this was impossible, but now you get to see something like proof. And so I'm going to highlight this one other quote here. So well, this is again from Penrose. He says these pure illusions. And he says the only ambiguity is the distance. And now, okay, so what he really meant is that when you look at it, you don't know the distance, but really you do have a strong intuition about what you believe the gradient to be. So we allowed ourselves even more freedom, that is to put the faces any way we want, in any angle we want. But even then, we couldn't realize this. But he was interested in this case, and that's why if you shade it, because you believe the gradient is the same, just like in flat shading in 3D graphics, where the color you see just depends on the gradient, just the direction, the normal vector of the face. That you can color them this way and you can draw them. But I think when you see that, it's sort of annoying that if you, because in Wikipedia, you see this is the icon of check cohomology. And that's what he did, right? He put a cover on the space, built this cohomology from the cover. He was looking at the nerve of the cover. But really, I think what he was really trying to do was develop a discrete de Rham cohomology, where he has really the gradient defined everywhere, and that's what you get interpretation of. And now you want to find a function, right? And so de Rham cohomology, right, will tell you, can be used, for instance, to tell you that there doesn't exist an antiderivative, or at least it'll do the opposite, right? If there's no hole in the space, you know that, and you have a continuous gradient, you can find this antiderivative. And so really, I think probably it should be the icon over here. And it's a funny little factoid is that he really should have done this because, you know, one of his secondary PhD advisor was Hodge. So he had like the pedigree to do it. All right, that's all I have to tell you. Thanks. Any questions?
still didn't fully understand. I mean, is there algorithm to test whether?
Oh yeah,
this
what's the
is a
algorithm?
regular
Yeah.
population?
Yeah, so
Well, and then in the end, are you defining the way to test for this impossibility to be?
no, so,
To
so
extend that to.
yeah, so that is finding a cycle is one way to give a certificate of
Right,
impossibility.
but
It's not known if there always exists such a certificate. This is amazing to me, but it's unknown. But there is, in some sense, a very simple algorithm to find if there exists any lifting. It's just solving one system of linear equations. What happens is, if you think of the lifting now as, instead of the way I did it as lifting of faces, you're lifting vertices, subject to the constraint that the faces are flat. So for every, if the face is a, let's just say it's a 5-gon, then if I were to triangulate it, I have to add 2 edges. That's going to be 2 linear constraints that have to be satisfied. That is, because I'm going to have 4 vertices and they have to be flat. Right? So, so I have some set of linear constraints to test if there exists any liftings, and it's just something like 3n. Well, what are there? 3n minus 6 edges minus the number of edges, right? So however many edges I am away from a full triangulation. And so you say, okay, well, so there's actually just some system of linear equations. There's some space, linear subspace of possible liftings. In fact, that makes sense also from the Maxwell perspective, like this linear subspace of equilibrium stresses. Like if you double the forces everywhere, everything is still in equilibrium. So it's clear, you can kind of start to see that you have this nice vector space. If you now ask for convex liftings, now what you're asking for is not that a fold is flat, but that it's bent a certain way. These are just linear inequalities. So now you just have this polyhedron of convex liftings. And so if you think of it kind of as linear programming, you're saying, I have a linear program with no feasible solutions. And so, you know, a certificate then is going to be something like some subset of constraints that can't be simultaneously satisfied. And so you can try to ask, do those constraints, what do they look like back in the geometry? Because they're going to be a subset of edges. And you can ask, maybe it is some kind of cocycle. It seems to be. But it's as far as I know, it's open. Yeah.
Can you use these techniques to show, for example, an alternative proof that Klein bottle doesn't bend in 3D, for example?
Oh, I see. Yeah. So unfortunately, this is not. You would like these kinds of obstruction results, right? And that's what I originally thought you would find, right? It says that if you read that that sentence I posted from Penrose, it sounds like, you're going to do a topological computation. You're going to find some object in there, which is going to be an obstruction to the existence of a lifting. But it's not. It's not the kind of result you get. In fact, it's saying that kind of, again, it's the
So it's
the
not
other
if and
direction.
only if it's a sufficient thing. It's not
Right. Because
vice versa.
right. It's more like, you know, if there's no hole, then you're always going to be able to do it. Yeah. Yeah. I thought there's another, actually, one other thing you can do with this, I believe, is there's this result about the Borromean rings that can't be realized with equal radius circles. You know, those are the rings where no pair of them are linked, but the union of all 3 are linked. And it can't be realized with flat circles of equal radius. And if you were to project it into the plane, well, you would see 3 ellipses. So if you imagine that someone actually gave you a realistic example of this, you'd get 3 ellipses. And from the ellipse, if you had to assume that it was from a circle in 3D, you actually know what the gradient through the plane of that circle is. Well, you know, it's either one way or the other, right? You need up to there's only 2 possibilities. And so you can think of the Borromean rings again as almost another instantiation of the same impossibility result.
Other questions? All right, so let's thank Don again.